Hello, everybody out there. My name is Simon Muff. I'm Business Development Manager at Keysight Technologies for the design software. And I talk today about the simulation of the conducted EM emissions from a buck converter. So first, I want to show you the references. You can have access on the internet to every of these shown material, and then set it up by your own with using a test license of Advanced Design System, for instance. I show you the schematic, how to set up the simulations in Power Integrity Pro with our fast FEM technology to use a simplified behavioral model and run the PCB extraction to get fast to the conducted EMI simulation results. And of course, we compare them to measurements. So this work is based on a December 2021 publication of modeling the conducted emissions of a synchronous buck converter shown in the IEEE transactions, and we've taken as this LMG 5200 by Texas Instrument is publicly available and you can download. I show you later. We have also shown the material here on the Design Methodology Conference for Power Electronics and IEEE 1 as well in Bath in September this year. And you see here the schematic of that one. It's a half bridge, basically standard usage configuration from a topology perspective, and let's say with a typical switching behavior. The rise and fall time is 3 nanoseconds, and R on is about 4.7 milliohms. So as said, the references, so you can go to the TI webpage, download the PSpice transient model, download the design files, and of course also the PCB design file. And let's say this is what we show here. If you go to the links here in the presentation, you can have access to a test license of either PE Pro or PI Pro. I show here the conducted emission with PI Pro, and let's say the description of the whole experiment and the board and so on is also much more material available if you want to dive deeper into on the bug experiment description shown here for similar types of the one shown here. So what do we simulate basically? We want to have a very fast judgment of the conducted EMI emission. So let's assume we don't have even a SPICE model for our transistors. So we just take the port of the input voltage, the output voltage, and the respective decoupling. We neglect the gate driver circuits to a certain extent. Of course, they can all be modeled accurately, but as said, we want to be here as fast as possible. And this is from the schematic of that documentation of the LMG 5200, the power stage, and we only take as said input and the output stage respective. So the flow is very, very easy. You launch PI Pro after you have imported the layout, checked the stack up. We use ODB++ format, usually in directory format or in file format. That doesn't matter. We support also all other major vendors of PCB design data on the market here. Then you do the simulation setup. I want to shortly show here the setup check first. You see here a perfect conductor below. For conducted EMI, sometimes you need to model that, for instance, for a power electronics modeler in our side. For the power integrity modeler, this is done automatically. This has to do with the port setup in FEM, respectively fast FEM simulation, because of the port reference. Would lead a little bit too far here, but who's interested, don't hesitate to contact us and we can elaborate on that a little bit more. Here the user does not need to take care. This setup is done usually automatically, and basically what you need to define here, you see on the right side the respective board, and I marked here by just clicking the input connector, and you have, as you see in the middle, just to drop that down to a voltage regulator module, and you can assign it as a power connector, and you get in, for instance, the 12 volt. That's all what to do. So a few seconds work only. A little bit more complicated it gets if you drag down then the switch, for instance. You set the VRM type, and you see here we support all VRM types, power connector which is used, and discrete buck VRM in that case. And then we define the switching voltages on the input and the output side. And with that discrete buck VRM model, you see here there's an upper switch and a lower switch. So this is that behavioral simplified model. In case you don't want to dive into the spice modeling of such a device, and you just enter then the respectively set the rise fall times with the 3 nanoseconds, the output voltage you desire, and the R on, what you usually have from the data sheet. In that case, it was 4.7 milliohms. And let's say then it's all done automatically, basically the frequency plan. And then you just have to select the offboard options you want. For instance, here we offer an automated compliance standard test bench just generated by a press button solution. And you do here the following in terms of setting the offboard options, and you can include the resistive losses in the ground. So here we do CISPR 25, and we just define the cable length. So that's it, because you press simulation, and let's say with that kind of setup, it's very, very fast. So within minutes, with fast FEM technology, you get a spectrum. This doesn't tell you anything really about if you pass or not. And this is what I mentioned. We have an automated generation of the CISPR 25 test bench, for instance. So you press the button only, and you have the test bench in front of you. It looks like that. So on the left side, you see there's the listen modeled, the switches modeled, and this here offers you also the opportunity to replace these switches by a spice model if you want. Yeah? So here you can go and just go ahead, because you see on the upper right there is a separation between the external, what I magnified here, for the harmonic balance simulation we run, and that same is of course also compared to transient simulation, much more time, because you just simulate the respective frequencies you want to have. And on the right side, you see all the components on the board and the S parameter extraction of the layout. And this is all generated automatically. So you don't need to wire that manually. And you can directly then here also press run your simulation. And then you get basically your setup here in terms of the respective look at all the CISPR 25 relevant emissions, the input currents, the load voltage, the switching behavior, the spectrum of these. And you have, of course, also, as you can see here on the upper row of the emission spectrums, the borders included where you have violations. Of course, I mean, how does this fast methodology, even without a spice model, where you can get to your results within 5 to 10 minutes, plus a little bit of modeling, then you are there. And how does it compare to measurements? I mean, what the advantage of simulation on that way is, you can easily, for instance, you see on the left side, split up in the differential noise spectrum and in the common noise spectrum. So you can then directly see where it hurts you. And here from the switching frequency at 1 megahertz, we see a violation. And if you compare the simulated to the measured data as mentioned, published in this IEEE paper in December 21, you see that we have a pretty good agreement between the simulated data at that respective frequency and the measured one. An additional advantage then, of course, is you can debug in simulation your design. Look whether this is coming from the switching, is it coming from the routing, and you can see all these layout effects by extraction by that. You can make it more accurate, of course, if you replace the shown behavioral models by a spice model and just do the same. Here we focus, of course, because the accuracy is pretty good on the behavioral fast approach. I mean, you have that results with the harmonic balance simulator within minutes really, and with the field plots you can easily how to say improve your design. So this shown methodology here gives you a big advantage versus how to say running EMC based measurement hardware cycle, seeing you failing, you have to add additional filters and so on, or change the layout, and here you can virtually prove your design very fast before you tape out and build the hardware respectively. I hope that was interesting for you. So looking forward now to your questions with respect to the Q&A session we're running. Thank you very much, and I hope you have an enjoyable Bodo White Bandcamp event in 22 here after the pandemic. Thank you very much.